Every galaxy we observe contains a massive, invisible gravitational distortion pulling on its stars. If this invisible mass, what we call dark matter, didn't exist, the entire galaxy would simply fly apart. But despite making up most of the universe, it remains completely hidden from our instruments. For decades, we tried to find it by building massive detectors and waiting for a dark matter particle to crash into an atom. But after years of searching, those direct collision experiments have repeatedly come up empty. Now, a new strategy is taking shape. Instead of waiting for a violent impact, scientists are tuning their instruments to listen for a faint whisper, a subtle, rhythmic pull that dark matter might exert on the very fabric of matter. Scientists now suspect the solution to this cosmic mystery lies in our ability to measure time down to its smallest possible fractions. This is the core of an optical atomic clock. Using elements like strontium, it measures time by tracking the microscopic oscillations of atoms as they move between energy states. It is the most precise measuring tool in human history. These clocks are so sensitive, if you lift one just a few centimeters off a table, it ticks slightly faster because it feels the Earth's gravity weaken. Operating such highly delicate equipment is a constant battle against the environment. Every laser, lens, and sensor must be perfectly aligned to maintain accuracy. On the Earth's surface, that sensitivity becomes a liability. These clocks pick up every piece of ambient noise, from passing traffic and temperature shifts to the bombardment of cosmic radiation. An instrument sensitive enough to feel the faint pull of dark matter is effectively blinded by the chaotic noise of everyday life at the surface. To solve this, researchers are taking these room-sized clocks and moving them deep inside mountains. Facilities like the Modan Underground Lab in France and Bedretto Lab in Switzerland sit beneath 1.5 kilometers of solid rock, providing an environment of extreme isolation. Millions of tons of granite act as a natural shield, slashing the flux of cosmic radiation hitting the lab by a factor of 1 million. The rock also provides a seismically dead environment, stripping away the vibrations of human civilization. Utilizing the Earth's crust to isolate these instruments creates a zone of deep silence, the only environment quiet enough to detect the universe's elusive signals. The primary target is ultralight dark matter. Theories suggest it behaves less like a solid particle and more like a massive invisible wave washing through the galaxy. As this wave passes through ordinary matter, it temporarily alters fundamental physical constants, such as the mass of an electron or the strength of forces holding an atom together. To detect this, scientists run two different highly stable systems side by side, like a strontium clock and a silicon cavity, and compare their frequencies in real time. Because the dark matter wave affects these two systems differently, they will briefly fall out of phase with one another as the wave passes through the room. Physicists measure this resulting frequency shift at a resolution of 10 to the negative 18, equivalent to a 1-second change over 30 billion years. In the absolute silence of an underground lab, an atomic clock stuttering or losing time offers significant evidence that dark matter has finally been found. By running these comparisons underground, the GILA team has already established that the coupling strength of dark matter to normal particles is less than 1 part in 100,000, the most precise boundary ever set. The next major leap in this emerging field is the development of the world's first nuclear atomic clock, which uses the isotope thorium-229. By measuring the transitions of the ultra-stable nucleus instead of the outer electron cloud, this clock becomes vastly more immune to electromagnetic noise and stray fields. Scaling these hyperstable nuclear clocks turns the Earth itself into a planet-sized dark matter observatory, capable of monitoring the entire galaxy's weather. While we once looked exclusively to the stars to find the universe's missing mass, the search is moving into the deepest silences on Earth, where our most fragile instruments can simply listen. Dive deeper into the hidden secrets that shape our reality. Click the subscribe button, activate the bell, and see you in the next scientific investigation, only on TEMBODocs.